guys, and I want your feedback, I want to consult you with it as well. This is my plan for the rest of the integration unit. Okay, so it's a short unit, and I have said, we're going, we're rolling, thank you. I have said that vectors took a bit longer than I wanted it to. Okay, vectors took a bit longer than I wanted it to, but we did it very thoroughly. We've got a very comprehensive understanding of vectors, which is good. Integration is short. We've done a lot of it in methods, and all we're doing in spec is learning a few more techniques and one more application, which is, what's the application we learn? Rotating around the x-axis, okay, which is part of the methods assignment anyway. So, here's my plan, right? So today we're doing 7b, which is a horrible exercise to name. What we're doing is integrating to the inverse trigonometric functions. Thursday 7c, integration by substitution, is a technique we learned to perform integration. And then on Friday, integration by parts. All right? And I don't want us to sort of stop there, okay? Because I think, like, if we stop there, it's sort of an odd place to stop and we come back for a lesson. So my plan is to make videos for both of these things, all right? For you guys to work through in the first week, okay? Those two exercises in the first week. And then, in the second week, I've got, we'll do some revision, all right? And I've got two optional tutorials for you to attend. So the first one being on Friday, 22nd, so that's in the second week at 2 p.m. And the next one being on the Monday of term 3, week 1. It's a student-free day, so it can have you guys come in at 11. All right, so both optional, opportunity to pop in and ask questions, which we put the test on Tuesday, which is our only lesson for that week. All right, because then you guys go on retreat. And I think that's going to be the best way for us to order this unit, okay? And I'm open to discussion with you guys. But if we're not doing this, then these get bumped to sort of do one here, and then we'll end up doing another one in week 2, and then we've got some revision lessons, and all of a sudden we're sort of doing the test at the start of week 3, and we've lost a lot of time and momentum, like things are just disjointed up. So that's my proposal. I think it's very accessible, and my promise to you is I'll be here for the tutes, and I'll be on emails ready to answer any questions you have. If there's a very important question, I can even make a video about it. So I want to support us to get this unit done so we can focus on differential equations. I think this is going to be an easier unit, all right, compared to differential equations where we're going to want to dedicate a fair bit of time. All right, so that's my plan at this stage, and I'll let you guys sort of dwell on it, and I'll come and consult you guys individually as we're making our way through the lesson. Okay, the next thing I want to talk about is the Massa quiz night. So this is a Ripper event. All right, so 10th of August, 7 until 9:30. So the school is actually organising a bus, which is fantastic. So there's a couple of sort of junior teams going. So juniors team is year 7s and 8s. The middle teams are 9s and 10s, and then the senior teams are 11s and 12s. And so what that means is, you know, you guys will be competing against a number of other schools in there's 50% maths, 50% general knowledge. It's lots of fun, it's a great night. It's in Penola for us. So it happens all across the state, but the local one for us is in Penola. And what do you have? You have teams of 4 students. So what I would like us to do is maybe, I think nominate at least 2 teams from here, team for the boys, team for the girls, or so forth. So it'd be great if we can get, you know, this whole class to go along. The best of the best, hey? So that's my formal invitation. And I think Mr. Denise has prepared like an EdSmart form that I can send out to you folks so that they can get you along. All right, so keep that in the back of your mind. So that's August the 10th, so about a month from now. Excellent. Okay, so then what we're going to do today, I'll turn Vivi off. Today's exercise is on 7b. There we go, you were right, here's one. Although this might have some different questions. Today's exercise is on 7b. and I'm going to split it into two parts, okay? The first part we're going to do in 7B is just do the examples. Is that our fun? I'm bloody deaf. I'm so deaf. Is the examples. And the reason we're going to do the examples first is because that's all you need to know how to do to complete this exercise. It's quite easy, the examples, but then I'm going to offer an explanation of it, all right? And the explanation can be a little bit complex. So I'm going to do that at the end, but all we technically need to be able to do is to perform the integration. Okay, so again in 7B, we are just following rules. So let me write the examples up here quickly. So, am I right? Perform the following. We have -3 on the square root of 16 take x squared. And then for B, we go up here, we have 15 on top of the square root of 1 on 25 take x squared. And then for C, we have the integral of 5 on top of x squared plus 25. Are they all correct so far? Yeah, this is the old book. I made a few minor changes.
C is negative.
That's a negative?
The whole thing's negative.
The whole thing is negative, thank you. Very good. Okay, so let's just perform these 3 rules and then I'll run that out and put the last one up there for D. So we've got a number of rules here, right? And we've got to try and recognise which one does it resemble. Now, if it has a negative, we should try and use the rule that's associated with the negative, although they are both the same, as we'll see with their graphs in a moment. So it says perform this integral. So I'm looking at the rules up here, and I'm going, in this position I have 16. So it's not 1, so it's not anything from the first box. It can resemble something from the second box though, can't it? I could express it like this, as 3 times the integral of -1 on top of the square root of 4 squared take x squared. Okay, now we've written it as it's presented, the left-hand side of the bottom box. Alright? And so then what that's going to integrate to, this 3 is hanging out the front, and it goes to arc cos of x on top of a, and then smack that plus c on the end. Now, what I was saying before about the negatives, right? If you're looking at this negative, you're saying, I could pull that negative out the front as well. I could have pulled -3 out the front, okay, and then performed the integral a little bit differently, all right? If you look, when we don't have a negative out the front, it's this one up the top right here, isn't it? All right, it's the exact same. And so what you'll see is arc sine of x on a is equal to the negative arc cos of x on a. But what I want to say is, when there's a negative, we should try and use the negative rule, all right, unless we have to pull it out the front. So that's all well and good. I'm going to leave that negative inside the brackets. Okay, next one, we have 15 on top of the square root of 1 on 25 take x squared. All right, again, we'll pull that 15 out the front. We have 1 on 5, we have 1 on top of 1 on 5 squared take x squared. All right, 1 on 25 is 1 on 5 squared. Oh, there's a square root there too. And so that's now resembling the one at the top right, isn't it? And so what's it going to go to? The 15 hangs out. Arc sine of x on top of 1 on 5 plus c. And then that will simplify to 15 arc sine of 5x. So x on top of 1 and 5 will simplify to 5x. Alright, so there's B. Here's C. -5 on top of x squared plus 25. So I'm going to write it, I'm going to pull that negative out the front this time, and what we can see is we've got 5 on top of 5 squared plus x squared. Okay, that would be an alternative way of writing it. And now we've manipulated it so that it resembles the one in the bottom right. So this is going to evaluate to, the negative is going to hang out the front, arctan of x on A plus C. Right. Clear this off? No, okay. On D, we've got the integral from 0 to 1 of 1 on top of the square root of 1 take x squared. Okay, so the difference here is we have a definite integral, right? We have a boundary. So when we integrate, we're not going to have plus c. Let's have a quick squiz at our rules. All right, this is just going to be the top rule, isn't it? 1 on top of square root of 1 take x squared. There's no numbers involved. That's all it is. We can integrate this straight away. It goes to arc sine of x from 0 to 1. Okay, so that's going to be arc sine of 1. Take away arc sine of 0. Now what this means, right, what is arc sine? But it's the inverse sine function. Okay, so I've written that, that's written at the bottom on the page over here. Arc sine of x is the inverse sine of x. So it's inverse sine of 1, take inverse sine of 0. And what does that mean with regards to the unit circle? Okay, what it means is what angle is going to give us sine of 1. Alright, so rather than saying what is sine of pi on 2, it's saying what's the angle that gives us the sine value of 1. Alright, so if we go up here, that's the sine value of 1, that evaluates to pi on 2. And this one, sine of 0, where does sine of 0 occur? Here. So it's pi on 2, take away 0, our answer is pi on 2. Alright, and we always consider the smallest positive argument. Okay, so let's, I'm going to rub that out and I'm going to go through an explanation of what these things are. So I've drawn a few things I want to talk about. We're going to recap what inverse functions are, because so that's what you're doing in this exercise, right? It doesn't seem too bad, just a bit of substitution following the formulas. But let's explain what's going on here and how we derive these formulas. As well. So, the first is to do a recap of what an inverse function is. Alright, so remember an inverse function, if we have some function f of x, then f minus 1 of x is the inverse function. An inverse function will only exist if the function is 1, 2, 1. Alright, what does that mean? Each x value has one unique y value. Has to pass both the vertical line test and the horizontal line test. Okay, do we remember that? I might do a couple of sketches quickly. Alright, so if we have this function here, alright, we can see it passes the horizontal line test. Alright, that is, it only crosses the function once, and it passes the vertical line test. However, if it were to extend up here, alright, all of a sudden it doesn't pass the horizontal line test because it crosses the function twice. So this is no longer has an inverse. For it to have an inverse, it must be 1 to 1. Now, what we're doing here, so 1 to 1, was there any other properties of inverse? 1 to 1. And like, yeah, let's draw the inverse now to illustrate it. So if we consider the function sine of x, right, it goes like this. And I'll even come back here and draw it as well. And so you would say straight away, this does not have an inverse function. It doesn't have an inverse function because it fails the horizontal line test, right? However, one thing we do with functions is we can restrict their domain. And so if we restrict sine from minus pi on 2 to pi on 2, alright, if we restrict it over that domain, all of a sudden it has an inverse function, okay? The inverse exists from minus pi on 2 pi on 2. Alright, now if we are to draw an inverse, firstly, what's the coordinates of this point here?
Pi on 2, 1.
Pi on 2 and 1. X is pi on 2, y is 1, and this point here is going to be x is minus pi on 2 and minus 1. Alright, so one way you can generate the inverse, there's a couple of ways you can generate the inverse on your calculator. Let's do it manually first. We've also got to consider the line y equals x, right? Because what is the inverse but the mirror image of the function about the line y equals x? So I'll just check my scale here because I'm quite likely, yeah. So I'm going to just move this a little bit. Here. Alright. It's not much better. Okay, so the line y equals x is like this. No, it's awful. I need to start again. The line y equals x. Alright. And here's the curve sine x. Alright, that's better. And then it's coming down this way like this, right? And we've established these coordinates are pi on 2, 1, and these coordinates minus pi on 2, minus 1. Alright, so that's all good. So for it to be the inverse function, remember we need to restrict the domain from minus pi on 2 to pi on 2. And what is an inverse function but a mirror image about the line y equals x? So if I'm going to sketch the inverse of this part, it's going to go something like this here. Alright, and it's going to stop there. Alright. Can you guys see that? Or should we'll get a different colour. Get that one. That's a bit better. Okay. What are the coordinates of that point? Correct. Yep, it just flips them, doesn't it? So it's 1 pi on 2. The x value is 1, the y value is pi on 2. Alright? And so then if we're still performing the inverse, crosses over here, and it's coming down to this point, and the coordinates of that point, x is minus 1, y is minus pi on 2. Okay, so if this is the graph of sine of x, then this red one is the graph of arc sine of x. What is arc sine of x? It is sine minus 1 of x. It is f minus 1 of x. Okay, it is the inverse function. Now it's important to note, arc sine of x, or sine minus 1 of x, is not equal to sine x to the minus 1. They are not the same, because what is this? This is 1 on sine of x. And what is that? Alright, so this is a bit of a recap of 11 spec. It's cosec of x, isn't it? Alright, so if you look at the previous exercise, these are what we call the reciprocal trig functions. I restated them there for you. Excellent. Okay, so that's what we're doing here. Right, that's what we're moving from. That's what the arc sine of x function is. Okay, so all I'm doing there is defining that. Okay, next let's prove one of the rules. Any questions, sir? All makes a bit of sense? Cool. Excellent. Alright, so let's prove it. So let's just start with the first one. We're going to prove that the integral of 1 on the square root of 1 take x squared with regards to x is equal to arc sine of x plus c. Okay, it wants us to prove that this is true. So what we're going to start with, let's start with the function y equals arc sine of x. We can have the plus c there, but we don't need to. And let's try and differentiate it. We're going to try and differentiate it. So if we're going to start with this, I'm going to rewrite it in a form we're probably more familiar with. You can use either. Either of these is absolutely fine. Now, one way, if we were trying to solve for x, or if we were trying to graph the inverse function, is we can apply sine of x, or sine to both sides, sorry. So we're going to have sine of minus 1 of x. Okay, remember sine is a function, it's something we can apply to both sides. Now what's going on here is we have f of minus 1 of x. So who can remember, what does that evaluate to? X, perfect. This evaluates to x. Alright, so if we have sine of minus 1 of x, this side becomes x, and this side is y. Alright, so that's the definition of the inverse function, right? We've flipped it, we've flipped the variables around, okay? Remember on our graph, we swapped the x and y values. Okay, so we've got that statement. Now what we want to do is differentiate it, okay? Because how do we prove an integral? But we start by differentiating something, and then we make an integral statement from a differential statement. So if we want to differentiate both sides, what we're going to do though, first let's just swap them so that it's just because it's a little tiny bit neater. So let's perform the derivative with regards to y, to both sides. I'm going to differentiate both sides with regards to y. It's an equation, we can do anything we want as long as we do it to both sides. So over here we're going to have the derivative of x with regards to y. And over here, if we differentiate sine y with regards to y, what's it going to be? What's the derivative of sine x? Okay, let's think about it like that. What if we differentiated sine x with regards to x? Okay, what's that going to be? Cos of x. When you differentiate sine, you get cos. So what if we differentiate sine y with regards to y? What's it going to be? Cos y. Alright, so over here we've got cos of y. So that's just in brackets. Cos y. Now, one way we can express cos y is the square root of 1 take sine squared of y. Right, so 1 take sine squared of y would be cos squared of y, and the square root of cos squared of y would be cos y. Alright, so that's the legitimate operation. So what have we got? We've got dx on dy is equal to this. Now, if we form the reciprocal of both sides, if we flip both sides, we have dy on dx is 1 on the square root of 1 take sine squared of y. We're almost there, there's one more step. What is sine of y? Sine of y is x. So I might just rub that out to perform that substitution. When I perform this substitution, I've got 1 take away x squared at the bottom here. Okay, so what we've shown is that if this is the function, then this is the derivative. Therefore, integral statement, if we integrate this is what obtains. Okay? So that's a proof for it. There's heaps of those proofs in there. And I think in the start of this exercise, it gets you to have a go at some of them. So you're following the process reasonably similar to that. Excellent. All right, so that's all from me, big one. Let's get started.